All right, Human A&P, we're going to go over cardiac output, stroke volume, heart rate, and the factors that influence all of those things. Let's get right into it. So the definition of cardiac output is it's the amount of blood pumped out by each ventricle in 1 minute. So it's the amount of blood that's going out the ventricles, out the pulmonary artery, and out the aorta in 1 minute. The equation to calculate cardiac output is cardiac output equals cardiac output equals heart rate times stroke volume. So this is a little more information about what end diastolic volume and end systolic volume are. So this is a graph. Now, if you haven't seen my video on the pressures, go watch that because that will help you understand kind of what's going on here, because this is the exact same graph that we're using. Here, now we're just talking about volumes, okay? So the volumes, so with end diastolic volume, the volume of blood is greatest at the end of diastole. So this line is going to represent our volume, and our volume is going up, up, up. And then once we get to isovolumetric contraction, our volume's at the highest point it's going to be because the ventricles are full of blood, right? They're full of blood. They're ready to expel it out their respective arteries. And then once we hit the isovolumetric relaxation phase with this line indicating the low volume, this represents end systolic volume, because end systolic volume is the amount of blood that is left at the end of a systole. So given that a person is healthy and has a healthy heart, at the end of systole, most of their blood is going to be expelled out either the pulmonary artery or the aorta, and there's only just going to be a little bit left in the ventricles. So that's what end diastolic volume is and end systolic volume is. And the difference between the end diastolic and the end systolic volume is going to be our stroke volume, which is represented within this gap right here, difference between end diastolic and end systolic volumes. All right, so these three definitions right here are the factors that can affect the end diastolic volume and the end systolic volume, which will ultimately affect our stroke volume, which will ultimately affect our cardiac output. So preload, the definition of preload is the degree that cardiac cells are stretched right before they contract. Contractility is independent of the preload, and it is just the strength of contraction. And the afterload is the pressure that the ventricles overcome to eject blood. And we'll go over what all that means in just a second. So if we increase the preload, we increase the amount of blood that can come back and fill the heart. So what does that mean? Well, an increased preload results in an increased end diastolic volume, thus increasing the stroke volume. So when we exercise, blood is obviously, well, just in any scenario, blood is always going to the heart and it's returning back to the heart to be pumped out to the body. Well, that concept is called venous return. And when we exercise, we increase the venous return and we increase the amount of blood that is coming into the heart due to exercise and due to increased sympathetic stimulation. So when we're exercising, the heart, more blood comes and it fills the heart, it fills the ventricles. And that is exactly what preload is the amount of blood that fills the ventricles before contracting and ejecting the blood. So what do we mean by increasing the EDV? Well, let's just say we take our stroke volume equation. Stroke volume equals EDV minus ESV. And let's say the homeostatic range of the stroke volume is, we'll say the end diastolic volume is 60 and the ESV is maybe 30. That equals 30. But when we exercise and we increase venous return, the end diastolic volume, which is the 60 right here, it's going to go up. So in this case, since we're exercising, it could be stroke volume equals maybe 70 minus 30. And that answer would be 40. So you see how the stroke volume can go up with an increased EDV. And then ultimately we plug this 40, put it in here, and then whatever our heart rate is, and then the cardiac output will increase as well. So another way we increase our stroke volume is we increase the ventricular filling time when we have a decreased heart rate because of increased parasympathetic stimulation. And this is going to increase the end diastolic volume. Okay, so basically what this is saying is when we have a low heart rate and we're chilled out and we're under a lot of parasympathetic stimulation, just relaxation, we have more time to fill the heart with blood, which increases our preload, which increases our end diastolic volume, which then increases our stroke volume. And depending on what the heart rate is, the cardiac output could also increase as well. So another factor influencing stroke volume is contractility. Okay. So we have when more calcium enters the cell due to exercise and due to sympathetic stimulation from the sarcoplasmic reticulum and the extracellular space, this is going to lead to increased contractility and more blood being ejected from the heart, which increases our stroke volume and then decreases the end systolic volume. Because when contractility is stronger, we're able to eject more blood from the ventricles out, which is going to lower the amount of blood left in the ventricles at the end of systole, which increases the increases the stroke volume. And to prove that to you, again, let's say we have our homeostatic stroke volume with the end diastolic of 60 and end systolic of 30, which equals 30. But with increased contractility, thanks to our sympathetic stimulation, thanks to our increased calcium, now our stroke volume is going to look something like this: 60 minus 10, and that equals 50. So now you can see how our stroke volume increases because our end systolic volume number decreased, giving us a higher stroke volume, which when we plug it into here, depending on what the heart rate is, the cardiac output will increase. Now, how exactly does the calcium lead to increased contractility? Well, here is the physiology behind it all. We have our norepinephrine, which activates a beta-1 adrenergic receptor on a myocyte, and then that activation causes a whole pathway to occur. It causes the activation of the G protein, which activates adenylate cyclase. ATP converts into CAMP. So you can see that right there. ATP converts into CAMP, and then that CAMP activates a protein kinase. And then that protein kinase will increase the amount of calcium channels on the SR opening up, which causes more calcium to come out. And it also is going to cause more calcium to go through voltage-gated calcium channels on the plasma membrane of these myocytes. And that is going to cause more calcium release from the SR, more calcium from extracellular fluid, which increases the amount of calcium binding to troponin, and then it increases the cross-bridge binding for contraction. And all of that is going to increase the force of contraction, which will decrease the ESV. So the way that the afterload can affect the stroke volume is that, first and foremost, it's minimally going to change the stroke volume, minimally going to have an effect, unless there is hypertension present. If there's hypertension, the ventricle's ability to eject blood will be affected, which will increase the ESV and decrease the stroke volume. So what is hypertension? Well, hypertension is the amount of pressure that the ventricles have to overcome to eject blood through the pulmonary artery and through the aorta. So whenever ventricles are pumping out the blood through here and through here, there's always going to be pressure that's going back against the ventricles. It's always going to have to overcome that pressure gradient. That's why you want to have a very high pressure here and a low pressure here. You want a high pressure here and a low pressure here so that the blood can follow the pressure gradient. But if you have too high of a pressure that's going back against the aorta and going back against the pulmonary artery, then the ventricles are going to struggle to get this blood out. And that is going to cause hypertension. And so you will not be able to get as much blood out of the heart. And that is going to increase the end systolic volume. And so instead of the line being here, the line will be somewhere like here. And so that is going to cause the stroke volume to be decreased if the end systolic volume is increased. So for example, let's go back to our let's go back to our example. So here's our homeostatic EDV, and here's our homeostatic ESV. So that's 30. Now let's say because of the afterload impacts, because of hypertension, we now have, that'll be the same, and we now have the ESV increased. We'll say it's like 50 now because of this hypertension, which gives us a difference of 10. And so now you see how the stroke volume decreases when the end systolic volume increases. And so this 10, you then plug it into here, and then depending on your heart rate, the cardiac outputs would go down in this case because you're decreasing the stroke volume.